video later. Yeah, take it.
Okay. Okay, so hi everyone, we're the Medial Axis team. I'm Gonzalo Vegas. I also have Kavia, Lolita, and Jessica Hernandez. Jessica had a conflict, so she's not coming join us today, but she is also like a key component of our team. So the purpose of our main task in this semester was to implement the Medial Axis transformation for buildings. And the Medial Axis is this magenta set of lines and curves that you can see here, giving an input of these black lines and regions. We want to calculate then the magenta that we can see in this image. So, first, why the Medial Axis? So, the problem, the overall problem that we have with buildings is that most of them are unique. And what I mean, like most of them, they're like not exactly the same as the other one, and they can be quite distinct. And they're also made by humans, and they're like made for humans. So that makes it quite more difficult to study in a systematic way. So what the Medial Axis provides is like an automated routine to have a representation and a structure of what's the interior space of the building. And that, as you can see here on the right, it captures the circulation structure because you're able to reach every single part of the building to the Medial Axis, and which I call the partitioning structure, since each of the inflections of the Medial Axis has some information about how the space is being folded, we could say, into like a one common interior space. In addition to that, also is quite useful because it makes like a transformation of a 2D space into like a one-dimensional representation, which we can take it as a graph, while also preserving essential information of the building. So you can, in theory, go from the Medial Axis into a building and from the building into the Medial Axis in a clean way. Now the further like application that we can see having this structure complete, so we can enable some data-driven type of further applications. So, for example, to predict social information in the building, like the levels of rooms, or to classify and generate or predict buildings themselves. So our objective then is to implement the Medial Axis transformation for polygons with holes. We represent buildings here as a generic term of polygons with holes. A polygon being the other polygon, the overall boundary, and the holes are the obstacles. We want for like vector representation, which is a bit more complicated than a raster one. If we wanted to be very robust to highly symmetrical geometry, which is a very common problem in complex computational geometry problems like this, and because buildings that can tend to be very symmetrical. And we also are aiming to develop this for the Rhino Grasshopper environment, which is the common platform in architecture that we use for this type of issues. So we had actually two parallel efforts here. One is a Seagull port made by Kavia, and one is based on the Pi Voronoi made by me and Jessica. So Kavia, if you're here, you can go ahead.
Sorry, my Wi-Fi dropped on the building I'm in, but so for the Seagull port specifically, there were 4 main components to it. So I basically wanted to create like a framework that anyone could use to take any Seagull function they wanted and create a Grasshopper component with it. And so the first layer was the native C layer. So this was just a C program, and you would have the Seagull library installed in whatever computer that you're using. And then this would specifically just compile that Seagull components that you specified that you want used from the library. And it would create an application binary interface, which is just a compiled program that the computer can then read. And then the next part to it was you would have a native interop project. So this was a .NET project, and all this did was just call the Seagull commands from the ABI using a method called platform invocation. But this specifically, you would just pass in whatever the Seagull commands expected. So if it was ints, you would pass in ints, or if it's like doubles, you would pass in doubles. But the .NET Bridge project is where all of it really came together. So you would call the Seagull functions that you specified in the native interop project. And then what would happen is that you would use that function and pass in other variables, so you would modify it. So if you're using Rhino, sometimes the primitives types that they use in that is a little different. So you would have the .NET Bridge project basically combine whatever you type of input you want to pass and then call the function and then create the output that you desire from that specifically. And then finally, you would just have like a console or grasshopper component that would then call that function. And then this is, you could just test it out in your console project or just have a grasshopper component that you could run and use that Seagull command on. So if you go to the next slide, I just have like a little diagram. It's basically the same thing as the last slide, but here specifically just showing how all of the pieces connect together. All of the .NET projects were in .NET 7, since Rhino specifically, it only is compatible with .NET 7 so far. It's not compatible with any of the higher versions yet. And then if you go to the next slide, yeah, or the couple of next slides, I have pieces of the code actually just tied in together, showing exactly like if you have the very first one, that's just your C program calling the component or function from the Seagull library. And the next part to it is you would have specifically just your native interop layer calling that. And then after that, you would have the platform invocation method specifically and how that's being loaded in. And then if you go to the next slide, it's basically calling that in a grasshopper component. And then it's the final one is just a grasshopper component working as well. And then if you go to the next slide, so for the next future steps for this is specifically right now, it can't take a just the basic Seagull command. So I made it with the Euclidean distances. And for creating the medial axis transformations, we need to port the 2D Voronoi segments and then specifically just figure out how to get parts of the Voronoi segments, which would then help us create the medial axis transformations. So that would be the next part for this. Oh yeah, I think I jumped ahead a little bit.
Okay, thank you. Maybe a bit more of context. So, the Seagull is like a very popular computational geometry library, and one of the efforts was trying to bring that implementation of the medial axis into the Rhino environment. And the other one I'm going to show you now is like relies on a Python library called PyVoronoi, and this one takes like a more in a way, it's more simple since like it's already working on Python, which has its own issues and limitations. So I will now show you this. So here we can see in this screenshot in here this like Python 3 script is the where actually contains the computation of the Voronoi 2D, which is used to compute the medial axis, and all the rest are custom C# components from a grasshopper plugin that actually makes a calculation of the medial axis. So this script from Python using the PyVoronoi library is a port from the Boost C++ library that has many computational geometry applications. And what pretty much we're using here is that we are using a custom grasshopper script with Python, and so we can integrate to bring this capability into the Rhino grasshopper environment. And we pre-compute or we do some pre-processing of the input geometry, which pretty much any list of integer-based line segments. So I mean, like every point in the lines is made of integers, and that goes into the Python script, and that will output then the Voronoi cells. And the Voronoi, if you know, is just like the Voronoi from segments. In this case, is one of the more common ways to compute the medial axis. It's very similar to it, and it just has some additional geometry. So it's the common way to calculate the medial axis is to first calculate the Voronoi from segments, as we're doing here, and then filtering out some of the rest of the geometry. So I will show you more visually how that works. So we start here at the beginning. This is our input, in this case, house for the three-carrier house by Miss, and you'll have one boundary to be the polygon, and some holes which are other set of polygons that are inside our boundary, and this would be the description of our floor plan. So after we input this into the Python script, it will output all these collection of new polygons in red, which are the Voronoi cells. So each one of these is a cell this will be from the output itself. We will get the cells, and we'll also get what is the segment that created each cell. So, for example, this segment here created this particular cell, and this one here is created by this particular segment. And we have the information of the identifiers of the segments and the cells themselves. After we have the information, we input that into our Medial axis component for some post-processing to actually compute the Medial axis, which identifies the different types of vonoid cells based on what are the type of lines and their corners. Creates the Medial axis then from the intersections of the cells, and then creates a graph to represent the Medial axis based on its adjacency. Now output then the cells now identify the different parts of the Medial axis that we'll show later, and the edges of the graph. So these are the cell types. As you can see, we have 4 types. We have a convex concave, convex convex, convex, and concave concave. And what this means pretty much is the type of corner that is creating each of the segments originating itself. So going back to this here, this one is created by a concave corner and a concave corner, so it's a pink one, it's a concave concave. We have one specific one that's only convex, because this cell only touches the environment in one particular convex corner. Have the convex convex on green is created by 2 convex corners, and the convex concave, which is created by a concave in a convex corner. And we need to identify this. We have to make these categorizations, because after that we can use that information to then identify what are the different parts of the Medial axis. So this is the actual result. So each segment of the Medial axis here is generated from the intersection of 2 cells. As you can see, there's some additional geometry from the cell that you can see in white that has been filtered out in this case after applying this processing. And the way this works is that we need to identify what are the different parts of the Medial axis that are represented in each color. It might look similar to the previous one, but actually it's different. So in this case, this particular part, let's say here, which is a concave one. Actually, sorry, this might be wrong. It's actually the line part. It's created by this section of line and this section of line, which is reflected then in these 2 cells here, this one and this one, intersecting here in the middle. And we identify what are the different types of the Medial axis based on the types of cells that generated each pair of cells that generated each segment. So with this, then we can just make like a very simple adjacency check, and then we can then create the underlying graph to represent this. Just to visualize it, I representing with each part with a point and one into draw a line each edge. So it gives you like the underlying representation of a graph structure for the Medial axis itself. After that, then we can compute some measures on top of the Medial axis that can be useful for later applications. So this one is the maximum circle that is like a circumventing the environment. This is placed in semi-equal intervals along each segment. As you can see, it maximizes the size of the circle along the Medial axis. And this is pretty much like the underlying information that computes the Medial axis itself. From those same circles, we can also compute what are the lines pointing towards the 2 segments that creates the actual circle. So it gives you like an initial instance of what could be like a programmatic way of doing like a type of coordinate system for the Medial axis. This is in one direction, and you can do it in the other direction. I call Medial axis offset. So here we're in a way like scaling each of the Medial axis segments back into its original source line, and that will give you in this way this other direction of how to create this type of like coordinate system. And this also plays, as you can see, it also gives you like an idea of density. So we have the same number of lines being placed in sometimes quite large spaces and quite small ones. And we put them together at the same equal intervals. We can have more or less type of consistent way of describing the building, or like more like a grid made for this particular building. And this gives you, it's not perfect, it's like an approximation for now. So you can see some of the joints are not connected properly there, but it's like the initial step to have like a more proper description of the interior space of the building. So these are just some examples of this to showcase that this can work like pretty much in the most of the building have tested. There's some small things that need to be worked out. Sometimes we need to remove some additional cells that are medial axis part that are outside the building. So a bit more of work is necessary to have a completely clean description. But in this very complex plan, you can see that the routine still works perfectly fine. So finally, for future work, so a couple more measures we calculate to better understand how the medial axis is working in the building is to calculate the rate of change of the radius in each of these circles, so we can understand, for example, how much space opens or becomes more narrow as you traverse the medial axis. We can also complete the convex map, which is a space syntax type of approach from the medial axis in an automated way, which can be quite difficult. And later on, we were planning on encoding like a social information, so how this space is used into the medial axis, so then we can convert this undirected graph into a directed acyclic graph that will contain more information based on how the building is actually used. After that, we can then start thinking about training a neural network based on this, a graph neural network based on these medial axis graphs, so we can predict buildings results. And that's it from me. Thank you.
Thank you, everyone. Thank you, Gonzalo, Kavya, and Jessica, although she couldn't be here today. Really great work.